Welcome. My name is Nico Lindström. I'm from Finland and University of Turku. And I'm presenting you our group's work of wearable ring-based system for measuring hemodynamic parameters. So a bit of motivation. Hypothalamic tension is a global health burden affecting over 1.4 billion adults globally and increasing the risk of cardiovascular disease, reducing quality of life and putting heavy financial burden on the economy. The current methods to measure blood pressure include brachial cuffs and arterial catheters, and they are often bulky, complex, and expensive. The invasive methods, like the arterial catheter, have additional risk of infection, arterial injury, and bleeding, and it's not really practical in routine use, even if it's clinically very well done. So our provided solution. We made an easy-to-use, wearable, and easily available blood ring. So our ring uses local oscillometric spot measurements. And in oscillometric technique, we are increasing the external pressure of the artery above around the artery to reduce the flow of the blood until it's fully occluded. During this process, the pulsation increased to maximum amplitudes and then decline. The maximum amplitude of these oscillations align with the mean arterial pressure, usually called MAP. This is my Finnish pronunciation. Around these peaks, systolic and diastolic blood pressures can be determined by using different algorithms. So a bit about the ring itself. We decided for the form factor of the ring because it's easy and simple to use. Well, not simple to use, but easy and simple and comfortable. And it has an easy location for the finger, base of the finger that has the digital artery, which we can occlude. Our device has two different PCBs. The main PCB contains the necessary electronics for the sensor units and the system on chip. Then we have a flexible PCB that contains the sensor unit. This whole system is operated through PC and the graphical user interface. So a bit about the device. It's probably broken. So the ring is made from two different parts. It has outer sleeve and the inner guiding push. The outer sleeve is a spiral shaped and it turns the rotational motion of the outer part into vertical movement, and then it pressures the digital artery. The guiding push basically holds the piston still, which allows the rotational motion to turn it into the vertical movement. And our sensor unit is embedded to the piston. So a bit about, so as the piston presses against the digital artery, this is how we are getting the oscillometric response. So our PPC module is commercially available. It's MAX 30101. Yes. And it works as the light source for infrared light and the photodioide detector. And underneath it, it's portions to the resistor. So a bit about the software and firmware and a bit more about the device. So our graphical user interface is based on YQT framework and allows the user to control the LED values and also storing the data as CSV files. This firmware is running on ESP32 system chip, and it's programmed using C language. The firmware takes commands from the user interface, which allows the user to change the device settings and control the parameters measurement process. Sensor data is streamed through via serial communication and is visualized in the user interface as pressure, PPG signal, and the target slope of the pressure. Yes, so we're using PPG and pressure modulation. So the sampling rate of this system was 100 Hz. So about the flow of the measurement. First, the user will set the values for the LADs and begin the sampling process. Then the user rotates the outer part of the ring while trying to stay close to ideal pressure ramp indicated by the user interface. This was the correct ramp was tested and through trial and error. The sensor and the data, the sensors send data to user interface where they are displayed and saved. The ring is turned until we are reaching about systolic blood pressure, and then it's turned back to the original. We got the permissions for the small human study, where we took 10 volunteers, all healthy, 5 of whom were women. The mean age was 26 plus minus 3 years. And we took 3 to 6 measurements to have as much good quality data as we could get. Our reference device was brachial cuff and Umbro, which was Umbro Mark II. So during the protocol, we first identified the correct ring size because our sensor is very sensitive for the sensor position. Then we identified the digital artery by rotating the finger underneath the finger around 200 degrees. And the digital artery is where we get the highest signal amplitude. After which, the healthy volunteer stayed still around 15 minutes to make sure that the blood pressure is stabilized. The measurements were performed in keeping the arm at the heart level, so there would be any hypostatic effects. So what pipeline we used. So first, our raw signal was inverted, so to ensure that the systolic peaks are facing upward. Then we performed a Butterworth bandpass filter between 0.5 and 8 Hz to get the pulsatile AC signal to data. Then we did Hilbert transformation and took the absolute values to get the envelope. And from the envelope, we detect peaks of the PPG signal. To these peaks, we fitted the 10-degree polynomial fit. And based on this peak, we took the corresponding pressure values. The amplitude ratios for systolic and diastolic pressures are usually trade secrets, so we trained a small model to give our good estimations for these parts, these parameters. For systolic blood pressure, our value was 0.24, and for diastolic, it was 0.82 of the maximum values. And the maximum value was mean arterial pressure. So about the results. The purpose of this study was to demonstrate that we can get the oscillometric measurements done by using only simple wearable. And we were able to get some moderate quality oscillograms. And then we performed Bland-Altman plot to analyze the agreement between the reference and the proof of concept device, which shows quite a bit of variation. So in conclusion, despite slight differences or moderate differences between the reference and pilot device, we were able to measure the blood pressure using only a wearable ring. And this version is prone to error from temperature, thickness of the skin, sensor placement, which is really important in this one, and non-linear movement of the ring rotation. So what we can improve on this device is fine-tune the mechanical system and do some simplifications to overcome the most prevalent issues, which is that our sensor is really sensitive on the sensor placement and rotational of the room. Thank you.